Analytic Geometry by Charles Lehmann.
Chapter 6, The Parabola, Section 53, Introduction. In his previous work in elementary geometry, the student has studied two curves, the straight line and the circle. The same curves have already been considered from the analytic viewpoint. We now begin the study of plane curves not ordinarily included in a course in elementary geometry. We start with the curve known as the parabola. Section 54, Definitions. The equation of the parabola will be derived from its definition as the locus of a point moving in accordance with a specified law. Definition: a parabola is the locus of a point moving in a plane so that its distance from a fixed line in the plane is always equal to its distance from a fixed point in the plane and not on the line. The fixed point is called the focus, and the fixed line the directrix of the parabola. The definition excludes the case where the focus lies on the directrix. Let the focus and the directrix of a parabola be designated respectively by the point F and the line L, as shown in Figure 74. The line A passing through F and perpendicular to L is called the axis. Let the point of intersection of the axis and the directrix be designated by A. Then, if V is the midpoint of the line segment AF, it lies on the parabola by definition. This point is called the vertex. The line segment, such as BB', connecting any two distinct points on the parabola, is called a chord. In particular, a chord passing through the focus, such as CC', is called a focal chord. The focal chord LL', perpendicular to the axis, is called the latus rectum. If P is any point on the parabola, the line FP drawn from the focus F to P is called the focal radius of P. Section 55, the first standard equation of the parabola. We shall see that the equation of a parabola assumes its simplest form when its axis is at the origin and its axis coincident with either one of the coordinate axes. Accordingly, consider the parabola whose vertex is at the origin and whose axis is coincident with the x-axis as shown in Figure 75. Then the focus F lies on the x-axis. Let its coordinates be p, 0. By the definition of a parabola, it follows that the equation of the directrix L is x equal negative p. Let P, x, y, be any point on the parabola. From P, draw the line segment PA, perpendicular to L. Then, by the definition of a parabola, the point P must satisfy the geometric condition, equation 1, the length of FP is equal to the length of PA. By Theorem 2, Article 6, we have the length of FP is equal to the square root quantity x minus p squared plus y squared. And by Theorem 9, Article 33, we have the length of PA is equal to the absolute value of x plus p. Hence, the geometric condition, equation 1, is expressed analytically by the equation the square root of the quantity x minus p squared plus y squared equal the absolute value of x plus p. If we square both sides of this equation and simplify, we obtain equation 2, y squared equal 4px. Conversely, let p sub 1, x sub 1, y sub 1 be any point whose coordinates satisfy equation 2 so that y sub 1 squared equal 4px sub 1. If we add quantity x sub 1 minus p squared to both sides of this equation and extract the square root, we obtain for the positive root the square root the quantity x sub 1 minus p squared plus y sub 1 squared equal the absolute value of x sub 1 plus p, the analytic expression of the geometric condition of equation 1 applied to p sub 1. Hence, p sub 1 lies on the parabola whose equation is given by equation 2. We will now discuss equation 2. in accordance with Article 19. Obviously, the curve passes through the origin, and there are no other intercepts on the coordinate axes. The only symmetry which the locus of equation 2 possesses is with respect to the x-axis. If we solve equation 2 for y, we have equation 3, y equal plus or minus 2 times the square root of px. Hence, for real non-zero values of y, p and x must agree in sign. Accordingly, we consider the two cases, p greater than 0 and p less than 0.
If p is greater than 0, all negative values of x must be excluded, and no part of the locus appears to the left of the y-axis. Since no positive values of x are excluded, and since y may take on all real values, the locus of equation 2 is an open curve, which extends indefinitely far to the right of the y-axis, and above and below the x-axis. This is illustrated in Figure 75, and the parabola is said to open to the right.
Similarly, if p is less than 0, all positive values of x must be excluded in equation 3, and no part of the locus appears to the right of the y-axis. This is illustrated in Figure 76, and the parabola is said to open to the left. It is evident that the locus of equation 2 has no vertical or horizontal asymptotes. From equation 3, there are 2 points on the parabola, each having an abscissa equal to p. One point has the ordinate 2p, and the other the ordinate negative 2p. Since the abscissa of the focus is p, it follows, Article 54, that the length of the latus rectum is equal to the absolute value of the quantity for p. If the vertex of the parabola is at the origin, but its axis is coincident with the y-axis, we can show similarly that the equation of the parabola is equation 4, x squared equal 4py, where the focus is at the point 0, p. It can be readily shown that if p is greater than 0, the parabola opens upward, Figure 77a, and if p is less than 0, the parabola opens downward, Figure 77b. The complete discussion of equation 4 is left to the student. Equations 2 and 4 are generally called first standard equation of the parabola. Since they are the simplest equations of the parabola, we often refer to them as the canonical forms. The preceding results are summarized in Theorem 1. If the axis of a parabola is coincident with the x-axis and the vertex is at the origin, then its equation is given by the first standard form, y squared equal 4px, where the focus is at the point p, 0, and the equation of the directrix is x equal negative p. If p is greater than 0, the parabola opens to the right. If p is less than 0, the parabola opens to the left. If the axis of a parabola is coincident with the y-axis and the vertex is at the origin, then its equation is given by the first standard form, x squared equal 4py, where the focus is the point 0, p, and the equation of the directrix is y equal negative p. If p is greater than 0, the parabola opens upward. If p is less than 0, the parabola opens downward. In each case, the length of the latus rectum is given by the absolute value of 4p, the coefficient of the first degree term. Example: a parabola whose vertex is at the origin and whose axis is coincident with the y-axis passes through the point 4, negative 2. Find the equation of the parabola, the coordinates of its locus, the equation of its directrix, and the length of its latus rectum. Plot the locus. Solution. By Theorem 1, the equation of the parabola is of the form equation 4, x squared equal 4py. Since the parabola passes through the point 4, negative 2, the coordinates of this point must satisfy equation 4, and we have 16 equal 4p times the quantity -2, where p equal -2, and the required equation is x squared equal -8y. Also, by Theorem 1, the focus is at the point 0, p or 0, -2. The equation of the directrix is y equal -p or y equal 2, and the length of the latus rectum is absolute value of 4p equal 8. The locus, focus, directrix, and the latus rectum are shown in Figure 78.